Okay, so to start us off today, I am going to give you all some water. Are you feeling thirsty?
Yes.
Yes.
Hold on, I can't trust chemistry water. What kind of water are you giving us?
Fiji water.
The box says.
Oh no.
Jamie. The box says water cup.
Okay, so I'm giving you all a water molecule.
I have water.
Don't spill it, please.
Can I take it apart? Is that possible?
Can I take it apart?
Don't take it apart. It
That's
can
what
be
she
taken
means
apart,
by
but
spill it.
we
Why
don't
does it
want
look
an
like it's supposed to be some sort of
explosion.
Pokemon?
Just a face. I feel like this. It's magnetic.
Only on, because it's only on the center, right?
I feel like this should be magnetic or something.
Okay. All right, did everyone get a water? Sorry, it's not very much. It won't hydrate you very well.
Wait, can I eat it?
I'm sure just by breathing in.
I mean,
Yeah, I'm sure, right? Just in the air itself, even though we live in a dry climate. Okay, so we learned last time, so let's review and connect here. So why does water look like Mickey Mouse?
two ghosts.
Good, Seth, right? So there's two ghosts on it that are pushing the hydrogens down, causing it to have what we call a bent shape. Now, the other thing we didn't talk about last time is this idea of the electrons in the atom. So what I've done is I've put little beads on this model to help us visualize, okay? So each line, right, each stick represents 2 electrons. Generally, we say that those electrons are shared equally between the 2 atoms, but that is actually quite false.
He spilled.
Okay, they're quite fun. So these 2 electrons, can everyone see those? Rarely is it in shared equal relationship between them. They're still shared, but most of the time it's not very equal because one of them has a stronger pull towards electrons than the others. We're going to learn more about that trend as we go, but it's called electronegativity. Electronegativity is the force at which something can tug on electrons in a bond. So let's write this in and then we'll keep talking here. So our 2 little electrons, if it was equal tugging, right, if it was an equal tug of war, then the beads would be in the middle, right? Because if the green's pulling and the yellow's pulling with the same strength, they'll be in the middle. But if green has a higher electronegativity, meaning it's buffer than the yellow, then the electrons would get drawn closer to all the green atoms. That is what we call a polar bond, is when the beads are not in the middle, but they're one way or the other because it's pulling more, we call that a polar bond. Think of the word polar like P-O-L-E, of like a magnet, poles of a magnet, how like one side is negative and one side is positive. Because these little beads are negative because they're electrons, so if the green one gets them, green all of a sudden is going to become more negative, and the yellow would become more positive. Now, keep in mind, it's not like ionic, because it is still shared. It's just considered not equal sharing, right? It's probably like if you have a cookie and your mom's like, hey, share that cookie with your brother. So you'll break it, but it doesn't break equally, and then you give your brother the bigger half because you're the good person, right?
No. You would. I would just shove it in my mouth.
But you can still say you shared even if the cookie isn't broken equally. That's the same idea with the electrons. They still belong to the yellow. They still have an octet. It just, they're hanging out more on the higher electronegativity side, okay? That's what this arrow here, will you guys draw, this picture is supposed to be printed. You see a little blank space off to the side? Will you guys draw this picture for me really quick? So just draw an H circle and a CL circle. And then what I want to really draw is this arrow. I'm just talking Polarity and IMF. And then I'm going to do all the demo and stuff next time. Okay, so then underneath your picture, draw this arrow. ours are known as a dipole arrow. Do you remember what the prefix di means? Two. So it's two poles, so dipole. So two poles meaning a negative and positive. So that's why the back side of the arrow has like a plus sign. It's saying, hey, this side is positive, and the side that it's pointing to is the negative side. So what we end up with whenever you have a polar shift is it results in a positive side and a negative side, aka kind of like a magnet. It's not saying it's magnetic, but it has the behavior like a magnet in that it's positive and negative. Okay? Now, that's what it means when you're just looking at two things. So not looking at the whole molecule, but just looking at two things. Anytime the beads shift, that's a polar bond.
So if the beads, since where they are, from where we are sitting, does that mean the arrow would be going this way?
Perfect, yeah, good Cam. So what she said for those that didn't see is because the beads went to the green, in a sense the arrow would be pointing towards the green one. And then the left is in the middle. Good. So when we look at the entire molecule now to know if it is polar, is you have to look at the symmetry of it. Where if it is completely symmetrical, oh, sorry, let's define electronegativity officially. So I think there's a line right there to define it. So electronegativity is the tendency of an atom to attract electrons in a bond toward itself. So it is the stronger in the tug of war. Tendency of an atom to attract electrons in a bond towards itself. Just had the idea of the bead thing this morning, so that's why none of the other ones have beads on them, is because I just ripped this one apart really quick and threw beads on it. Thought it would maybe help in visualizing. So, okay, with this idea of electronegativity, once again, in our next unit, we'll spend a lot of time talking about this trend. Pretty much you just need to know this, okay, that the higher electronegativity pulls the electrons towards itself, resulting in a negative side and a positive side. This is the trend, actually, for electronegativity. So it goes, red is the highest, and green is the lowest. So there is this pattern on the table, where things on this side are always the buffest, and the ones on this side are the weakest, and then it varies in between. Yeah, go ahead. So we'll spend a lot of time kind of addressing that trend, but just in case you're wondering, well, how do I know which one?
Why is AU an outlier and MM?
Interesting, huh? We'll talk about it next unit. Because it's just gold, right? But yeah, interesting, right, that they go against the general pattern. Okay, so if we say a molecule is not, yeah, go ahead.
The white one's just not charged at all.
Yeah, so, oh, that works. I don't know which one you're taking here. Yeah, because these ones never bond, right, with things. If they don't bond, then they don't ever pull. And then these ones are just all the man-made created ones, so they've never really been
Tested?
yeah, because they don't live for very long. So, but you would expect these ones to probably follow the trend, right? If we could test them enough, but that's why. Yeah, good observation on that. So when we claim that something is non-polar, think not pulling, it's because it's equally balanced, meaning that all the electrons are going out or all the electrons are going in. So even though there's a tug of war here and there's a tug of war here and there's a tug of war here, if they're all equal, it's like the tug of war cancels each other out because the shape is perfectly symmetrical. Now, theoretically speaking, if one side, let's say this side wasn't a green and it was a red thing, and this red thing was really strong, and so it pulled these ones out, so these ones like this, now it is polar because it's not symmetrical, because one side is going this way, the other two are going inside, resulting in negative side, positive side. Versus if everything's getting pulled out, you don't have a difference of negative and positive, it's just all going out. Or vice versa, all going in. Questions on that? So what you look for in a structure to know if something is polar or nonpolar are these two things. Okay? So nonpolar molecules is when all the atoms bonded to the central atom are symmetrical. So once again, green, 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 if they're all the same thing. And they are no lone pairs. Now, any thoughts of why a lone pair would play a role in this?
Because there's no pole.
They don't have a pole, right? But what do they do to the shape?
They changed the shape because of
The ghost.
force.
Yeah, it can't be symmetrical when there is a ghost, at least with the shapes we've talked about. Some of the bigger ones they can be, but with all the ones we've talked about, anytime you add a ghost to it, it pushes the bonds down or in a different direction, and it's never symmetrical. So that's one big thing, is if you look at your atom and on the center is a ghost, automatically it has to be polar because the shape isn't symmetrical. Okay? All right, let's flip back and then we'll define polarity, or polar. Flip back with me to last time's table. There was a column that we skipped. So let's look through really quick with the examples that we gave and label if it would be polar or non-polar. So the first one was CO2. So looking at that molecule, give me thumbs up if you think polar, thumbs down if you think non-polar for CO2, or AB2, I guess we could just say. So AB2, polar or non-polar? If you give me a thumbs down, have a smiley face because you are correct. Label that non-polar, everybody. And let's, maybe some of us have our definition backwards. So what does it mean to be non-polar? Symmetrical, not poling. I think some of you maybe reverse the definition. Okay, let's look at the next one. So AB3, polar or non-polar? Show me your vote. AB3, polar or non-polar? So remember, what we're looking for is you first look for symmetry and you look for ghost. If there's no ghost and it's perfectly symmetrical, it's not polar. This right here, right, is trigonal planar. And so if all the beads are in or all the beads are out, that is not polar. Because in order to be polar, they have to be shifted on just one side. Okay, let's try another one. I think we're getting there. AB2E, which we drew the O3 molecule for, right?
For something to be non-polar and it says it has to have no lone pairs, does that mean just the central atom?
Yes, good clarification, Chatwin. So we only, just like with Vesper, we only looked at the central atom. For polarity, you're only looking at the central atom as well.
Okay.
Yeah, no, great clarification, because that might have been what was messing a few people up too. Okay, so the next one, O3, polar or non-polar? So that would be our bench shape. Imagine there's beads on here. Good, always polar. Because if the beads pull out, well, now we have negativity here, positivity here. If the beads pull in, you have negative here, positive there. Versus when you had one at the top, if they all pull out, negative, 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 you don't have a positive side. Okay, so that's in 3D space. So that's what you're looking for, is it all shifted or is it balanced? Good, okay, turn the page. Next one was AB4, our tetrahedral friend. Tetrahedral, polar or non-polar? Show me your vote. At least with the example that we gave there. Polar or non-polar? Non-polar. First thing, are there any ghosts on the middle? Nope. And with the example we gave, they were all Fs on the outside. Now, if it was like the one I made where one side is an F and the others are H's, this would be a polar tetrahedral because this is different than these three. So what you want to look for is different things on the outside or ghost on the middle. Do you have a question, Kristen? Oh. Yes, so yeah, this isn't a case of like tetrahedral are always, some things are always polar and then others are, they can't, right? Lone pairs are always polar, but if it doesn't have a lone pair, it can and can't be. So yeah, no, good clarification. Okay, trigonal pyramidal. Show me your vote, polar or non-polar. Definitely polar, has a ghost, right? Messes with the symmetry. Good. And then last one is the other type of bent. Polar or non-polar. Definitely polar. Good. Okay, now, with this idea of polarity, right, when we say something is polar, we are claiming that that substance has a negative side and a positive side. So if you haven't already, take your little water molecule, find a friend, and see how they interact with each other. Take your water molecule and see how they interact. Okay, sorry, I kind of got ahead of myself. So here's the little notes to write down for polarity. So if something is polar, we're looking for different atoms around the middle or lone pairs, right? Those are kind of the two things that will tell us for sure it's polar. Okay, so what did we observe with our water molecules? They connect because one side is positive and the other side is negative, and so there's a force that happens between them. Now, do the white sides ever come together? Why not? Yeah, they're both the same force, right? Or the same thing, the two red sides, and you can feel if you try to push them together, right? You can feel it repelling itself, right? Now, if something is not polar, like this molecule, has no polarity whatsoever, there's no attractive force. It doesn't stick.
Wait.
Pretty much in the models, there's no magnets inside of that one, right? So it just doesn't stick like the water molecules do. So that's one of the really cool things as we look about these properties is when something is polar, it causes interactions between the molecules.
This looks like some kind of bomb,
Yeah.
and I want to blow it up really fast.
It's not a bomb. I mean, I guess it is. I mean, that's not. The chemical itself is actually quite flammable, but that plastic model is just plastic.
Here we go ignite to the chemical itself. Well, everybody's in Disneyland.
What chemical is it?
Butane. So here's kind of another way you can visualize it. So with a water molecule like you have here, the red is showing the negative and the blue is showing the positive. And so that's what you get when something is polar. If something is not polar, when you look at these maps right here, it just ends up being all blue or kind of just like all grayish because it's just equally distributed. Oh, okay, so we brought up this question last unit. Why does water exist as a liquid at room temperature while carbon dioxide exists as a gas at room temperature? You guys kind of remember this question a little bit?
Different boiling points in the structure.
So they do have different boiling points, get deeper. Like what
Pressure.
we've just talked about.
Polar bonds
There must be something
in the bond.
that is holding them together. Because because liquids are close, right? Gases are spread out. So things that are liquid, there's something that's holding them together and it has to do with polarity every single time. Now, we have 3 different types of polarity and that's what we're going to define today. So your first objective is just being able to say, oh, I just swallowed like a bug. Yeah, or something.
Protein.
Protein, right? can is breaking it down into one of three types of polar. We have a temporary polarity, we have a permanent polarity, and we have a super strong polarity. So it's kind of like low, medium, high of polarity, and they have special names that we're going to assign them right now. But recognize it's all polarity. So what does it mean if something has polarity?
Means it's not even.
Good, it's not even. It has poles, so it has positive and negative sides. Okay? All right. So that's what intermolecular forces are. Intermolecular force describes a force between two separate things. Can I hold that for a second? I'm sitting here. Okay? So an intermolecular force is the friendship force.
The friendship.
Water molecule to water molecule, what type of force do they experience? Friendship. Is it strong friendship?
No.
Super strong friendship, or okay friendship?
It's like a decent acquaintance.
Okay, so there's the three types, right? Keep in mind though, it's between. It is not an actual bond. Okay, the force to get one of these off is way stronger than the force of friendship.
Wait.
That's like me ripping like your leg off versus like
Oh my gosh, that
you
makes
and
so
your
much sense how you got my hand off.
Okay, so IMFs are much weaker than the true bond. So keep that in mind that the dash between is the IMF. These sticks are not the IMF. The IMF is what happens between this and this. What force do they experience, if any? Are they friends? Are they kind of friends? Or are they really good friends? Okay? Keep that in mind though that when you only have one molecule drawn, it doesn't ever represent an IMF. Because an IMF has to show this to this.
Too small.
Okay? So if it only gives you one picture, think, all right, this with another one of them, what force do they experience? Okay, with this idea, once again, IMFs are what cause molecules to stay together. If things didn't have any IMFs, the world would not exist because everything would be a gas and nothing would stay together if it wasn't bonded. Say what?
What about gravity?
The gas is still, once you're a gas, gravity kind of doesn't.
Stars would exist.
Yeah, I mean, things would exist, but not, us as humans would not, because water wouldn't exist if you would die. So.
Oh, cool.
We could just breathe in the steam and rapid rate.
Suck it up.
We
Okay.
are.
Okay. Oh, yes.
If you go back to slide
I never did before, and someone in AP just this year brought the same thing up. And I was like, why? I was like, yeah. I forgot that was like, they're like, yeah, the associated like agency or something like that's who they are. Okay, good. So keep in mind, big picture is it's all about negative and positive forces every single time.
Be positive.
Okay? Technically, something does have to be negative too, I guess, in this case, but we want to be always the positive.
I will be the negative of this class.
Thank you for volunteering that. Okay, so the first, wait a second, I feel like something is out of order here.
Yeah.
We're missing dipole.
Oh, this is dipole, that's where, I just didn't see the header.
Dipole.
Okay, turn to the top of page 6. Okay, so the first type of force we're going to talk about is the middle. So this is the medium, this is like a good friend. Okay? It's known as, the label for it is, we call it a dipole-dipole force. This force happens when both things come with polarity. So if this comes with polarity, and the other one has polarity, then between them they can have a dipole-dipole force. So that's what you look for to identify this force, is say, all right, is this molecule polar? If it's polar, then it has a dipole-to-dipole force. Okay? All right, the next type of force is the weakest one. This is like an association more than maybe a friend. Okay, it's known as a London dispersion force. Okay. The guy's name actually was London. His last name was. So what a London dispersion force is it is a temporary dipole or temporary polarity, a temporary friendship. Okay.
So,
You and Brooke today, a temporary friendship. Okay. Now with
no
that.
offense, but,
So what does it mean to be polar again?
Charged.
Why is it charged?
Because it's not even.
Good, because the electrons are one way, right? So when something is polar, this side is positive and this side is negative, always. What happens with London dispersion is there's a momentary point at which the electrons are positive and the electrons, or one side is positive and one side is negative. The reason is this. Even though something may have a higher electronegativity, right? If the electronegativity isn't higher, electrons are not stationary things. They're constantly moving. Move, 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 orbit, orbit, orbit. So there could be a moment in time where all of a sudden the electrons choose to go to the
outside.
that side, making this side of the molecule negative and this side of the molecule positive. But it's not like it's being held there in the tug of war. So that's why it's temporary, because at the next moment they could easily
Reverse.
shift and go
Reverse.
the other way. But for that moment, while that side is positive and the other side is negative, they can feel an interaction with another molecule and have a force between them. That's why it's the weakest one, though, is it's not stuck, right? They don't stay in that position, they can easily shift back.
Also, every molecule.
Go ahead.
It's like if you had a bunch of people on a boat and you said, hey, everyone get to the side of the boat, and the boat moves and everybody
Love
starts
it.
freaking out and they run back to the other side.
No, that's a great, great visual, Preston. So what he said, for those that didn't hear, is imagine we're all on a boat and we all just run to the front of the boat because, I don't know, something exciting happened up there, right? It's going to cause unevenness of the boat, but then at the same time, we can easily all just run back. That's exactly what the electrons do, is they just are moving, and through probability, there's a probability that they could all be one way. Now, what's cool too, though, is actually the influence that can have. So imagine we're a boat, and the classroom on the other side of us is also a boat with electrons. If we all run towards the wall, what are we going to do to the electrons on the other side of the wall?
Make them go to the other.
Yeah, we cause them to kind of shift too, so you can kind of get like a domino effect. But once again, there's nothing holding the electrons in place. That's why the friendship can easily break, because the electrons just shift right back. Love that, Preston.
So do the actual atoms not have a lot of pull on the electrons themselves?
Yes. So normally in a nonpolar molecule, yeah, there's not a very strong pull one way or the other.
Okay.
Yeah, no, great connection as
So
well.
one more thing is
Yes.
is like what kind of polarity they are, is it like very determined by what atoms are in the molecule?
It's kind of a combination of what's there and then the shape of it as well.
Okay.
Yeah, but definitely, you definitely will find that certain elements are like always non-polar.
Okay.
Yeah, no, great connection.
So there is no cup labeled dishwashing detergent. There are none for you guys. These pipettes, yes, and there are pipettes labeled 3 different things, and it just says label.
Okay, put out what you can and then I'll figure out the rest.
Nothing everything's hypothetical.
So here's kind of another visual. So like this is how we sometimes think an atom is. But with a temporary dipole, we see that the electrons all of a sudden move over here and get distributed. Okay, so we have friendship force, which is dipole-dipole. We have temporary friendship, which is London. Now we have best friend force called a hydrogen bond. Okay, so a hydrogen bond is an extreme version of polarity. So it's just polarity again, but it's really, really strong. There's 2 factors that make it so strong. Okay, the first factor is actually kind of what Cam brought up, is what atom is in it. There are 3 atoms that have the highest electronegativity of all the atoms on the periodic table. Nitrogen, oxygen, and fluorine. Remember NOF, N-O-F. And they kind of like go right there
5,
in a
6,
line.
7.
Yep, 5, 6,
7,
and 7.
8, 9.
Oh, thank you, 7, 8, 9. Yep, so those three have very, very high electronegativities, meaning they always win the tug of wars. So what happens is if you have one of those in connection to a hydrogen, hence the name, hydrogen bond. So let's pretend this is water. So here's oxygen, here's hydrogen. Oxygen's gonna pull the electrons towards itself very, very strongly. If this is hydrogen, and I pull electrons away from hydrogen, it's only a proton left. Because hydrogen has how many electrons to begin with? 1. So if we pull away its only electron, you get a very, very positive force, a very, very negative force, hence your extreme polarity. But you need those two things. So in order to identify if something is hydrogen bond, you have to have hydrogen, but that hydrogen has to be directly connected to N or F. So first thing, check for hydrogen,
Then check
then
for NOF.
check to see if the H is connected to N or F. If not, it could just be a dipole, but it wouldn't be this best friend kind of force. Okay, so once again, the H must be directly bonded to one of those. Now, the name is slightly deceiving because it's not a real bond though. There's not a stick between the water to the other water. You can see right there in your little water molecules. But they kind of say hydrogen bond just because it is the strongest of all the forces. So, we'll talk more about this next time with our lab and the time after that as well. But just to get you thinking, you have probably, most of you have experienced the strength of a hydrogen bond if you have ever belly flopped into a swimming pool. That's why it hurts, because the best friends are holding hands against you. It's like a giant game of Red Rover and you lost.
Nice.
Is that why it's easier to jump into like white water because the hydrogen bonds are being disrupted?
Very good. Yeah, so if you've ever gone like and seen like the ski jumpers in Park City, has anyone ever done that? In the summer, you can watch ski jumpers jump into like, do tricks into a swimming pool. If you haven't, it's really cool. I think you can actually pay to do it, but I don't know if I dare do that. Can you? But what did they, with the water, is they break it up with jets, like white water, so that it doesn't hurt. That you can mess up your trick. You could belly flop, literally, and it wouldn't really hurt in comparison to other ones. So, yeah, great connection. Okay, questions on our 3 types of friends. Associations, good friends, best friends. Okay, let's kind of summarize it. So right there at the table, we're going to summarize all 3. Okay, so dipole, once again, this is our medium strength force. It's because, this is the big thing. Put a star in this box. The way you know who has this force is you look if it's polar. If it's polar, then it has to have dipole forces. Now, these forces can be additive. Something can have the friendship force, which also probably means it has the temporary force too. Because it kind of like builds upon each other. And then the closer they are together, the stronger this force can become. Everyone good on that one? Okay, London dispersion is our weak one because it's the temporary force. And this one's easy to label because everything has this force, because everything has electrons. So every molecule on planet Earth experiences some type of London dispersion force. Every single time. And it can get pretty strong if it has a lot of electrons to shift. So even though it's temporary, if you have a lot of electrons shifting, meaning a heavy mass, then it can be fairly strong force still. Alright, and then last one, hydrogen bonding. So with this one, you just gotta make sure you have N over F directly bonded to H. And then it's the greatest of all three strengths. And then even though we use the word bond, keep in mind it's not an actual bond. It's just a very strong force. Yeah.
Is it not real because it's like a magnetic bond?
Exactly, yeah, and the definition of a true bond is like a true transfer or shared of electrons, and there's no electrons in that friendship, it's just a positive and negative, so.
Is it FH or EH?
F to H. Okay, flip your notes over for me. We're gonna skip that next little section, because today we're just gonna practice the application side. So flip over to this table where it says which IMFs are present. I'm gonna do 3 of you to get 3 with you, and then you'll try 3 for some smiley faces to check it. Chapman, did you have another question?
Yeah, so if it's like just a proton, and the electron is, like, say water for example, it's just
Yeah.
a proton, and then the electron from hydrogen is on the oxygen, that's not taking up very much space, right? So that's why it's a liquid, is because they're really close together, is that right?
It definitely could be part of it for sure.
Yeah.
Because keep in mind that the only difference the difference between solid, liquid, and gas is really proximity of the things. Right? Is the closer they come together, the more likely it is to be a liquid or a solid versus if they're really spread out. So yeah, I'd say definitely most things with hydrogen bonding exist as liquids at room temperature because it pulls them so close together. Yeah, no, great connection. Okay, so I'm gonna do these 3 with you, and then this is what your homework looks like tonight. Is given a structure, can you identify what forces the substance has? Now, the first thing I would do when I'm doing these, and on your homework there's actually a separate column for it, but is identify, first off, if the molecule is polar or non-polar. So let's do that as a review really quick. So this molecule, thumbs up or thumbs down, polar or non-polar? Thumbs up, it is polar. How do I know? Yeah, circle the ghost in the middle, right? Ghost on the middle, always make it polar, because it just makes it not symmetrical. Okay, let's come to this one and then we'll go through our forces. Polar or non-polar? Good, non-polar. This one, polar or non-polar? You're going halfway. There you go. It is polar because that side is different from the other sides. Right? It's not symmetrical. The shape is, but one side is red and the others are green. Okay, now to identify the forces, I'm just going to pull this down. Maybe. Just kidding. I guess I could write up high. Okay, so how do I know if something experiences London force? Everything does, because it's all about electrons, right? Molecular nice, they're friends with everybody to some extent. So the answer is always yes. Check, check, check for London. Everything in the world has London forces.
So we can just say yes for everything.
Yep, whenever the question is, does it have London? The answer is always yes. Okay, dipole to dipole force, how do I know if something has it?
If it's polar.
What? Oh, so they're going to find something that doesn't have it.
Wait, what about like unit or something?
It does, they're just so weak. And because how many electrons, it's because of how many electrons it has, right?
Fair enough.
So, but yeah, it's still there, just barely a friend. Okay, how do I know if something has dipole forces? If it's polar, make a note of that. So dipole is if something is polar. So if something is polar, yep. If something is not polar, nope. I would put an X just to remind you that you didn't like accidentally like, yeah. Okay, how do I know if something has hydrogen bond?
If it's polar and it has
Hydrogen and
Good, so
NOF.
we need hydrogen with NOF, N-O or F. So first one doesn't even have hydrogen. Second one has hydrogen, but it's not N-O or F. Third one has hydrogen, has F,
But they're not directly bonded.
but they're not connected. They're not, so still no. Okay, try the next three. You can talk with your table buddy, and then we'll check them for some smiley faces. It's on their paper. I know, thank you so so you can see it. Try these three, set your pencil down once you have them done, and then we'll check it.
Jamie, do we have to do this?
I'll talk about that one, but not right now. I'm passing out, the packet got broken in half. So this is the other half of your assignments for this unit.
Wait. Oh, visualizing investment polarities.
What does that mean?
Like a lot of my friends just appear in my life, and I'm like, I don't remember where you came in, but you're here now.
Thanks, Cam.
See,
Feel real
so
well.
it has one less electron, but it's.
I know you can kind of everything. I don't remember where I met him because we never had any classes together.
And anytime something
Until now.
just a plus, obviously it's always not. Polar means positive and.
Oh, wow, that was.
Polar means just positive, just negative. So you can kind of use it as a shortcut, but if something has a charge, it's always.
The same amount. Hydrogen is all positive.
Okay, let's check this really quick. We got 2 minutes till the bell, and then I'll tell you what of your many papers you need to do tonight, okay? Okay, keep your eyes up here really quick, just so that you don't do your homework wrong. Okay, first one up here. So first up, you should put London for everything. Good. Okay, for this one, it is non-polar, so you should have an X here.
Hey
Yes.
Falcons,
No.
I'm just trying to do a bit more of
No.
an informal introduction, gotta mix it up.
If you got
Speaking
that,
of
you
mixing
have
it up,
smiley
let's
face.
do the same thing I do
This
every
one you
single
should
day,
have
the
yes.
morning announcements.
No.
Over the weekend, our Skylarks percussionists performed at the Day of Percussion. I hear it was a big hit. It's just some percussion humor for you.
And
Caitlin Gardner received first place in her marimba solo, and Edmund Fox received first place in
So
his
3
timpani
slides, so
solo.
one's my face.
Now listen up to hear next year's Student Council Student Body Officers. Our Student Body President is Max Bradley. Student Body Vice President is Lily Broadbent. Student Body Secretary is Caitlin Price. Communications Officer is
This
Trevor
is your
Wyatt.
homework for
Connections
tonight. There's a
Officer is
lot of other
Eliza
papers for
McMillan.
like more
Assemblies
practice
is
later.
Andy Bennett.
But this is the
Falconeer
one
is
that
Nate
says
Kimball.
visualizing polarity
Servants is Mia
Vesper.
Schubinger. And our
That's
Senior
the homework
President is
assignment.
Desi Whitehead. Juniors and any others interested,
Yes.
representatives
Yeah, I'll
from
make sure I
Utah
get it. I
College
haven't
will
made
be
it
here
yet, so don't
today
check.
at 12:30 to give presentations about
By the end of the day, I'll make sure it's
scholarships,
answered.
housing, and all things college. Check Skyward or your student email for more information.
Yeah,
Our
just that
talent show
one.
tonight at 6 p.m. Be there to see the best.
Yeah, so that other one,
Chat
Chatwin, we.
Plus, there's a marimba